students, welcome to lecture number 10 for the subject of VLSI design KEC 072. I am Dr. Raman Kapoor and I will be starting a new topic today which is related to dynamic CMOS logic design. Till now we have covered nearly 2 units of this subject. We have done the overview of VLSI design, we have done calculation of delays and what role interconnects play in a VLSI digital circuit. Now, we are going to talk about something related to the aspect of design, okay? And today we are going to talk about dynamic CMOS logic design. So, let us just first have a brief comparison how dynamic and static CMOS logic design differ from each other. Okay? Till now we have seen a few examples related to different aspects. We have analyzed different parameters, especially delay in a circuit, and the examples which we saw were mainly either of an inverter or some logic gates, but they were static circuits. Okay. So, what does basically a static circuit means, or what is the general structure of it, which is visible on your screen right now? It has a network of PMOS transistors, generally referred to as a pull up network, followed by a network of NMOS transistors, okay, which is referred to as a pull down network. Okay. So, PUN and PDN are the brief short forms of this pull up and pull down network respectively. These tend to work concurrently in a complementary fashion. Okay. So, when one is off, another goes on, when one is on, the other goes off. This is a typical CMOS static arrangement. So, all the inputs here, you can have n number of inputs, they are applied simultaneously concurrently to the pull up network as well as to the pull down network. They are tied together, basically the drain terminals of the PMOS and NMOS are tied together and one terminal is taken out, which is basically the output. So, output is a function of all the inputs which is simultaneously applied to both the networks of PMOS and NMOS transistors. The pull up network, which is generally PMOS transistors, is connected to the power supply VDD, while the pull down network is connected to ground or negative voltage VSS. Okay. This is why the PMOS network is known as a pull up network, because it tends to pull the output up towards VDD, and the NMOS network pulls the output down towards ground, that is why it is known as a pull down network. Okay. So, this is a typical static arrangement, right, where all the inputs are simultaneously applied to all the transistors, to both the your pull up network, which is only PMOS transistors, and the pull down network, which is only consisting of NMOS transistors. Now, we know that both these transistors, they are MOSFETs and they are unipolar. Unipolar means that conduction is only because of one type of charge carrier. In PMOS, conduction is because of holes, in NMOS transistor conduction is because of electrons, and PMOS turns on at negative voltages and NMOS turns on at positive voltages. The threshold voltage, the so called threshold voltage, above which the transistor is considered to be a closed switch, is negative for a PMOS network, your pull up network, and it is positive for the NMOS or the pull down network. So, whenever the inputs change state in such a way that all the NMOS transistors are on, or at least there is one path between output and ground via your NMOS transistors, your output is pulled down, and vice versa. If the input combination is such that there is a path existing between output and VDD via the PMOS network, the output gets pulled up to logic 1. So, this is the brief explanation how static CMOS works. Now, let us see what is the dynamic counterpart of static CMOS logic design. Dynamic logic, on the other hand, has two methods of obtaining the output. One of them is known as pre-charge and another is known as evaluation, and evaluation is done basis to certain condition. When certain condition is satisfied, the evaluation is done. Okay. These phases are basically controlled by a clock. Okay. If all the circuits share one clock, we are looking at a synchronous circuit. If different elements use their individual clocks, we are looking at asynchronous circuit. But We are not interested in differentiating between the role of the clock right now. We want to understand what is a dynamic CMOS circuit. So, we know that at first thing, dynamic CMOS circuit is going to have a clock which is not present in a static CMOS circuit, and the value, the polarity of the signal of the clock is going to decide which mode we are working on. Okay. We are either be in the mode of pre-charging and either we will be in the mode of evaluation. So, depending upon what is your clock signal is, we will either be charging or we will either be evaluating. Okay. So, these two different forms or these two arrangements or methods of dynamic CMOS can be realized in two types of circuits. Number one, the one on your left is known as the N type dynamic CMOS circuit, where you have a pull down network where all the inputs are being applied. Okay. All the inputs are being applied to the pull down network consisting of NMOS transistor, and this is followed by another NMOS transistor which is known as the evaluation transistor. So, in all our lectures, wherever we have the evaluation transistor going on, it is represented by ME. So, wherever you see the symbol of ME, we are looking at the evaluation transistor. Okay. So, there are two modes, one pre-charge and another evaluation, right. So, depending upon how you have connected your ME transistor, that transistor becomes the evaluation transistor. Okay. So, in the N type of dynamic CMOS circuit, you have a pull down network with all the inputs applied, right, and the evaluation is done by another NMOS transistor connected just below the pull down network. Apart from that, you have a pre-charging transistor denoted by MP. Okay. So, in dynamic CMOS, MP represents your transistor which is responsible for pre-charging. Okay. And what is it we are charging? We are actually charging this load capacitor CL which is connected at this terminal. Okay. So, drain of your charging pre-charging transistor PMOS and the drain of your pull down network tied together to form your output terminal, and a capacitor is connected across it which is known as a load capacitor. It is this capacitor which is basically doing all the dynamic action. This is what is being charged by the pre-charging operation. Okay. The P type counterpart of dynamic logic consists of a pull up network. All the inputs are applied to the pull up network, okay, and the pre-charging is done here by a NMOS transistor and evaluation is being done by a PMOS transistor. Okay. So, there is a PMOS transistor here which is doing evaluation, there is another NMOS transistor which is doing pre-charging. Again the charging is being done of the load capacitor. Okay. So, these are the two forms of arrangement, one N type and one P type which you can have for the dynamic CMOS logic. Okay. So, it is generally common because of higher electron mobility, we tend to use the N type MOSFET more than P type MOSFET. That happened in static CMOS also, and same is true in dynamic CMOS always also. Okay. So, the clock signal denoted by phi decides the mode of operation of your dynamic CMOS circuit. Okay. So, this is the example of your N type dynamic CMOS circuit. Clock is applied to the gate electrode of PMOS transistor which is a pre-charge transistor. Same clock signal is applied concurrently to the gate electrode of your evaluation transistor which is an N type transistor. Okay. So, you have two extra transistors here, one pre-charge transistor, another evaluation transistor. The gate electrode of these two transistors is connected together and connected to the clock signal, right. So, the clock is a series of signal which goes from 0 to 1 at a certain duty cycle. If you have a 50% duty cycle, it means it is 0 and 1 for equal amount of time. Okay. Plus you have two inputs A and B and another input C. Okay. So, this is some kind of an arrangement where you will have a series network of two transistor followed in parallel with another network. So, this is a 3 input logic function. this is going to implement A dot B plus C complement. Okay. So, these are in series here, A dot B in parallel with C. So, the logic operation which you are going to get at the output is going to be of that of A dot B plus C complement. Okay. So, when the clock is in this phase, right, when the clock is low, this is where your clock is low and this is where clock is high. Okay. So, this is alternating between low and high logic levels. Okay. When the clock is low, your PMOS turns on because its threshold voltage is either 0 or negative basically. So, whenever the clock goes low, your PMOS becomes active. There is a low resistive path between output and VDD. This is where you are going to connect your power supply. Okay. And this is ground. So, when clock goes low, between output and VDD there is a low reactance path, low resistance path. Okay. And there is an open circuited high resistance path here. So, output, there is no possibility of output going to ground. The only thing which can happen at the output is if I connect a capacitor here, this capacitor starts to charge. Okay. So, assuming that it does not have any charge at initially at time t equal to 0, it does not have any charge. So, when you apply negative clock or when the clock goes low, okay, the output capacitor, your load capacitor is start going to charge, it is going to go through a phase of pre-charging. Okay. So, it goes from 0 to VDD in a certain amount of time. After that, when the clock goes high in its next cycle, next half cycle, when it goes high, this output gets cut off from VDD. There is no connection left between power supply VDD and output capacitor or load capacitor CL. Right. Now, depending upon this logic connection, suppose A and B are 0, but C is 1. Okay. If I have this logic input combination present, from this point till this point there is going to be a low resistance path, this is going to be a closed switch. Okay. From here to here, and the clock is also high. So, this evaluation transistor turns on. So, now I have a path for the ground. Okay. Now, this capacitor CL starts to discharge through this path, and if this is my logic combination A dot B plus C complement, when C is 1 and A and B are 0, I should be getting a 0 at the output. Okay. So, this circuit is basically implementing A dot B plus C complement, and when A is 0, B is 0 plus this logic operation for this input should give me a 0, and this is what happens. Now, capacitor starts to discharge through this path and I get a 0 output. This is the evaluation phase, but now suppose that C instead of being 1 is equal to 0. Okay. Even though this evaluation transistor is on, between CL output and ground there is no path possible, because this is high resistance, this is high resistance, this is a open switch, this is a open switch. Okay. So, with this the output has no path to actually go to ground, or the load capacitor can never discharge, and in this logic operation when all three inputs are 0, I should be getting a 1 at the output. Okay. So, this is how when clock is high, the dynamic CMOS logic circuit is doing its evaluation part. Okay. So, now when CL was charged to 1 during pre-charging and the evaluation stage gives me logic 1 as output, there is no switching required. Okay. So, 1 remains at the output. This is the major advantage of a dynamic CMOS circuit. Switching only occurs when you have to go from 1 to 0, because pre-charging state already makes your output capacitor, your load capacitor as logic 1. Okay. So, when already logic 1 is present at the output and you need 1 as the output, you do not have to do any switching, no power is consumed, no switching power is consumed. Only when a transition at the output is required from 1 to 0, which is found during its evaluation stage, power or switching power is consumed. Okay. So, this is how a dynamic CMOS circuit works. It has two stages of operation, one is known as pre-charge, another is known as evaluation. Both pre-charge and evaluation are clock dependent. The polarity of the clock is going to decide in which mode of operation your dynamic CMOS circuit is going to work. Clock is low, okay. I am talking about the N type of dynamic CMOS circuit. When clock is low, PMOS turns on, output gets charged to VDD, output capacitor gets charged to VDD, okay. And when clock is high, PMOS cuts off and evaluation transistor, which is N type, turns on. Depending upon input logic condition or logic circuit which you are implementing, if your output is required to be 1, the value remains as it is, okay. And when the output is required to be switched to 0, then that evaluation also occurs. So, this is a small description of what I have told you till now. When clock is 0, the output node out is pre-charged to VDD, that is why we call it charging stage or pre-charging stage. During this time, the NMOS evaluation transistor is off because it turns on at positive threshold voltages and clock is negative at this point. So, the NMOS logic network is isolated from the ground by the series network of NMOS transistor. So, no DC current flows regardless whatever you have at the input during the pre-charging stage, does not matter what is present at the input, input can keep switching from 0 to 1 or 1 to 0, it has no effect on the output. This is the time when you charge your load capacitor. Okay. During evaluation, clock goes high to logic 1. Okay. The pre-charge pull-up transistor is off because it is PMOS, it goes off at positive voltages and the evaluation transistor is turned on. Depending upon the values which you have at the inputs and the composition of your pull down network, basically what it means is that whatever logic circuit which we are trying to implement here. Okay. A conditional path, evaluation is conditional. Okay. A conditional path between out and ground exists through the NMOS transistor and ground is created. Okay. If such a path does not exist, so depending on your logic condition, you do not want the output to go to logic 0 low, okay. You want the output to be high, then no change is required to be done on the output, because during the pre-charge stage your load capacitor is already charged to 1. This is how evaluation is done. So, for NMOS dynamic CMOS circuit, clock is low means pre-charge stage and clock being high means the evaluation stage. Okay. Now, this is how this your charging and discharging of output capacitor is going on. I will just label the signals here. This is your clock, this is input A, this is input B, input C and your output. Okay. So, the first signal which you have here, this denotes your clock alternatingly going low and high. This is input A, which can either be 0 or 1, same for B and C. So, at different instants of time you are seeing that your inputs is being either 0 or 1 and CL represents your capacitor. Okay. And now, see the output is not a sharply defined edge. This is because this is a purely capacitive output circuit. Capacitors do not charge instantly, capacitors do not discharge instantly. Depending upon your RC time delays, every capacitor is going to take a finite amount of time to charge and a finite amount of time to discharge. Okay. So, here starting initially when clock is 0, this is your pre-charge stage. Okay. This is your pre-charge stage when clock is 0. So, clock your output initially which is at 0 gets charged to VDD. Okay. Then when clock goes high, it starts to evaluate. This is your evaluation stage, right, and this alternates. This is again pre-charging, this is again, this is pre-charging, this is evaluation, okay, and so on. So, see at any instant of time during evaluation, suppose here your A is 0, B is 1 and C is 0, this is required to give logic 1. Why? Because the output which you are implementing is A dot B plus C complement. Okay. Here when all 3 go to 1 during evaluation stage, okay, so 1 plus 1 complement should give you a 0. So, this is where your capacitor starts to discharge. Okay. So, this is your output. Some features of dynamic CMOS circuit: dynamic logic has higher speed, it occupies less area. This becomes more evident when the size or density of the circuit increases. Okay. For 1 or 2 input circuit, there is not much difference between static and dynamic CMOS, but when the number of inputs increases, the circuit density increases, the amount of transistors you require considerably reduces, because your logic is only to be implemented by the pull down network and you do not need same number of transistors in the pull up network which you need in static counterpart. Okay. The NMOS pull down network implements your logic function. The noise margin, like in static CMOS design, here it does not depend upon the width, the transistor ratios. It has lower power dissipation, as I said, when the transition is required from 1 to 0, only then switching power is consumed. When the output is required to be 1, pre-charge already gives you 1, so no power is consumed. Okay. So, no static current path ever exists between VDD and ground. The load capacitance is substantially lower, which results in faster switching speeds. Dynamic logic requires clock, which your static circuit does not require. Okay. It is generally not advisable and not even possible to operate dynamic logic at low speeds, because if the speed of your clock is slower, right, your output capacitor might discharge even before your next cycle comes around. Right. So, we have to basically keep refreshing, keep maintaining the charge on your capacitor. Dynamic circuits are more sensitive to noise and timing errors. This we are going to see in detail later on, and they are also affected by charge sharing. These parasitic effects we are going to be discussing in subsequent lectures. Let us just quickly see how the dynamic CMOS inverter works. Okay. So, this is a circuit of a dynamic CMOS inverter. Clock is applied to your pre-charging transistor, pre-charging PMOS transistor, and same clock is applied to your evaluation transistor. Okay. And this transistor, so you need a single NMOS transistor for a logic operation. This is your input. Okay. This is where input is applied. So, when just to see the timing diagram for this, the clock can keep going high and low. Okay. So, this is your clock. Your input can go high, it can be low, okay. It can again go high and can go low. Okay. So, this is just I am making randomly. This is your input. Okay. I had marked it as Vp in the diagram. This is your input. The output, so when clock is low, your output charges. Okay. So, it charges here, this is 0, this is VDD. Here it does the evaluation part. So, charging, evaluation, and so on. Okay. So, this is how it is working. In the evaluation stage, it sees at some point of time that your input goes high. At this time, the capacitor finds a path between NMOS transistor, between ground and output, there is a low resistance path. Okay. So, the capacitor starts to discharge. Okay. And here you are going to get a low. So, when this is 1, this goes low. Okay. Same cycle keeps on repeating here in the evaluation stage. Okay. So, after some point of time when this goes 0, it again starts to charge. Okay. Then in the evaluation stage, it finds that your logic is 1. Okay. And in any stage, so let us talk about this half, where charging has turned your output load capacitor high. During evaluation, the logic is again, the input is 0. Okay. So, at this point there is no path between ground and output. Okay. So, the capacitor has no path to discharge. So, whatever was charged remains here. Okay. So, this is how the dynamic CMOS circuit is going to operate. Whenever clock goes low, capacitor gets charged to high voltage. Whenever clock goes high, it starts to evaluate. If there is a path between output and ground via the evaluation transistor and your NMOS logic, output goes to 1 to 0, otherwise it remains at 1. Okay. The performance of dynamic logic, the most attractive property of dynamic gate is its high switching speed. Okay. The reduced number of transistors result in a small value for load capacitance. After the pre-charge phase, the output is high. If the successive output is required to be high, no additional switching occurs. This I have already explained. The required pre-charge time can be decreased by making the PMOS transistor larger. So, when you increase the width of PMOS transistor, your pre-charge timing can be decreased, okay? But you should not make it as low that the capacitor does not charge to its required value, right. There is always some kind of a trade off in logic designing. You can make your PMOS transistor larger, which will give you a lower pre-charge time, might make circuits faster, but it can at the same time slow down your gates and increase the capacitor's load on the clock line. Okay. And it might also happen that if you reduce your pre-charge timing, okay, the capacitor might not charge to VDD completely. So, with this we conclude with this lecture, which was based on dynamic CMOS logic design. I have given you a brief comparison between the static and dynamic logic circuits. I have explained how a dynamic logic circuit works, taken one logic example and the example of an inverter. To summarize, there are always two stages. One is pre-charge, which occurs when clock is low, another is evaluation, which occurs when clock is high. If there is a transition required from 1 to 0 at the output, only then dynamic power gets consumed, otherwise logic 1 remains at the output. Okay. So, from subsequent lectures we are going to discuss various features of a dynamic CMOS circuit. So, this is where this lecture ends. Thank you.